The somber hummingbird, a tiny bird from Brazil, has the highest maintained body temperature of any animal that we know of. If your body was that temperature, you'd experience convulsions, brain damage, or maybe just die. A human with the metabolism of a hummingbird would need to eat about 80,000 calories a day to survive. That's because staying warm by making your own heat takes a ton of energy. And that brings up a paradox, because creating your own body heat is incredibly expensive. The largest animals on Earth have to spend most of their day just eating enough to keep their heat engines running. Most animals on Earth just use the heat outside their body. It's easier. If you ate like a crocodile, whose body temperature hovers around 32 degrees, you'd have to eat less than 50 meals a year. And that works just fine for crocodiles. So it got me thinking, if making our own heat takes so much effort and is so costly, why do we do it? Hey smart people, Joe here. Every organism on Earth, from the smallest bacterium to enormous elephants, break complex molecules into simple ones to harness the energy to sustain life. And using energy to move bodies and run the machinery of cells produces heat. Endothermic creatures are special because they create enough internal heat to keep their body temperature above their environment. We humans are endothermic, what you might call warm-blooded. But it's more accurate to say that we create our own heat inside our body. And we're also something else, homeothermic. We regulate that heat at a steady temperature. Now, for most of us, that's between 97 and 99 degrees Fahrenheit. Now, most animals aren't this way. Endothermy is only found in mammals, birds, and a few special exceptions. Most animals are ectothermic. They don't produce enough internal heat to stay warmer than their environment. And just like you have to constantly feed wood into a stove to heat a house, we have to shovel fuel into our own heat-making machinery. And that means food. A lot of food. I mean, most of the energy from what we eat is released as heat. And about 10% of your daily calorie intake is dedicated just for regulating your body temperature. And you might not realize it, but you think about making heat all day long, or at least that happens deep in the core of your brain. It's so deep that you aren't aware of the processes controlling your thermostat. Your body's thermostat lives here, in the hypothalamus. If your body temperature goes down by just 5 degrees Celsius, your brain starts getting a little fuzzy. Your heart loses its normal pumping rhythm, which is pretty bad news for staying alive. So our bodies work hard to stay warm from the inside out and maintain a narrow, safe temperature range. If you're too cold, your body does things like shivering to create muscle warmth. You stop sweating. Your blood vessels constrict to keep heat from radiating off the surface of your skin, and you get goosebumps, which might not seem that helpful these days, but to our hairy ancestors, that was a way to trap air in our furry insulating layer. But if our bodies get too far above their narrow optimal range, you basically turn into this egg. Heat unwinds the very structure of proteins in your cells, and you could die. So if you're too hot, your hypothalamus triggers your blood vessels to open up and all those little hairs lay flat, and you start sweating, drawing heat from your body through evaporation, the same way that blowing on hot soup cools it off. Your body is constantly turning these cooling and heating systems on and off to keep your temperature steady. Most animals that make their own body heat regulate their temperature in a similar way, but the ideal temperature for that thermostat can vary a lot. Compared to other endotherms, I'm pretty cool, just saying. What I mean is that the human body temperature isn't that warm. The hottest 20% of endothermic mammals keep their bodies higher than 37.9 degrees Celsius. And birds are even hotter. They typically run between 40 and 44 degrees Celsius. Warmer animals, they have to eat more. A 10 degrees Celsius increase in body temperature means 2 to 3 times higher metabolism to maintain. When heat is added to a body, it speeds up the kinetic energy of its molecules. Everything made of molecules speeds up, and so do the reactions inside your cells. Carbs, proteins, and fats are used up faster, and so is ATP, your body's battery power. So you have to eat to replenish that molecular fuel. For us, that means more trips to the fridge, but to any animal that has to hunt or forage for its own food, that means spending even more energy just to keep your thermostat steady. In the eye of evolution, keeping a body warm is expensive and kind of risky, so there must be a good reason to do it. Why do we go through so much effort just to keep ourselves warm from the inside? why do most reptiles, amphibians, fish, and insects get to live without spending so much energy just to be alive? Well, that story goes back about 315 million years. And like a game of blindfolded hide and seek, it's a story that starts cold and gets warmer. At first, all four-legged vertebrates were ectothermic. Their body temperature changed according to their surroundings. And the first step to changing that was a literal step. When amphibians first wiggled their way out of the swamps and walked onto land. The move to land brought new challenges. Near the end of an era called the Carboniferous, Earth started to cool. We call it the Great Drying. Water got locked up in glaciers, the forests shrank, and drier habitats popped up in their place. Now, to survive in this drier world, animals had to evolve new adaptations. Things like holding your body up without the aid of buoyancy. You had to save your water and not dry out under the hot sun. And these all required higher metabolism. This is also when we think animals first started chewing, allowing them to draw more energy out of the plants and prey that they consumed. If you run your tongue on the top of your mouth, you'll feel another innovation on the path to warm-bloodedness, the secondary palate. It's what separates the nasal cavity from the mouth. Okay, what does that have to do with being warm-blooded? Well, unlike early amphibians and reptiles, you can breathe through your mouth or your nose, meaning you can breathe and eat at the same time. The secondary palate opened up more time for chowing down because, you could breathe while you did it. Well, here in the Permian, we also start to see the first evidence of walking on two legs. And moving around on two legs turns out to be a lot easier if you're warm-blooded. The big muscles required for bipedal motion require more energy, and to sort of rev up your body's engine that high, you need to be able to make your own heat. So if I didn't make my own heat, I couldn't do this, at least not for very long. No animal exists on Earth today that can run fast, far, whose temperature is less than 30 degrees Celsius. Cooler muscles just can't move as fast. There's only one modern reptile that can even run on two legs, the Jesus Christ lizard, and it's more of a sprinter than a marathon runner. Then, about 252 million years ago, Earth experienced its worst extinction ever, the Great Dying. About 70% of the species on land went extinct when huge volcanoes released carbon dioxide and methane into the atmosphere. Temperatures skyrocketed and oxygen plummeted. The animals that survived and took over afterward were the ones that could grow fast. And in large part, that meant animals with a higher metabolism and higher body temperatures. We used to think dinosaurs were more like lizards today. These lazy, scaly things that you're more likely to find basking on rocks out in the sun. But we now know that dinosaurs were much more like birds and mammals. They grew fast and they moved in ways that suggest they could stay warmer than today's reptiles. Some large dinosaurs might have handled this just by being huge. Think about it, a swimming pool isn't gonna lose heat as fast as a cup of tea. So the largest ancient reptiles could have stayed warm even if they weren't entirely warm-blooded. Consider that the Komodo dragon, the largest lizard alive today, is able to maintain a relatively constant body temperature compared to its smaller relatives just because it's big. But it's harder for smaller animals to stay warm compared to big animals because they have to work harder pound for pound than a big animal to maintain the same temperature. Which is why we think full endothermy, or warm-bloodedness, first arose in something small. And that happened because this happened. About 66 million years ago, the sky basically fell down. Most big animals died because they couldn't duck or find cover, and they just got roasted. Small animals were more likely to survive, and a lot of them were capable of making their own heat. Animals like Schrödinger. Yeah, this is our best guess at what the first placental mammal looked like. Schrödinger was small, about the size of a rat. And the bird line of dinosaurs made it too, because they were small. Over time, they got faster, better at running, and eventually even took to the skies. And it turns out flying takes a lot of energy too, so being endothermic would have helped. We tend to think of endothermic and ectothermic animals as two sides of a coin, as if you're one or the other. But we're discovering exceptions all the time. Some sharks can maintain a body temperature higher than the water that they live in, and so can other fish like the opah, and the tuna can too. And the hedgehog tenrec, an adorable little mammal found in Madagascar, is essentially ectothermic, or cold-blooded when it's not breeding. their temperatures can plummet to -2 degrees Celsius without lasting damage. So warm and cold-blooded is a spectrum, not a red and blue binary. But this still doesn't solve our paradox. Being endothermic is a lot of work. Remember, so much work that many endothermic species spend most of their time eating just to feed this engine of heat and survive. You would think that evolution would have pushed us large animals back in the cold-blooded direction, but it hasn't. Some of the answer might just come down to chance. When a big rock fell from the sky in the last major extinction, the things that survived that apocalypse just happened to be the things that were on their way to being totally warm-blooded. Those species were able to take over the Earth that we live on today, because they were what's left. But even though creating their own heat is incredibly expensive, it can have some unexpected benefits. I mean, without it, well, we might not be able to survive in as many habitats and climates on Earth. We also couldn't move around as much, and we'd be smaller, and that would be dumb and boring. And some scientists think if we weren't warm-blooded, we wouldn't have enough extra energy to raise and nurture our young. I mean, crocodiles aren't winning any Parent of the Year awards, okay? So being this hot is hard work. And to be honest, exactly how the history of life led to warm-bloodedness, well, there's still a lot more we need to learn to answer that question. Evolution doesn't really have a destination. It's the journey that's important. And it's a good reminder that there's still plenty of big mysteries of life to solve. Stay curious.